Hello everyone. Today I will introduce our video titled PWM modulation and demodulation. Pulse width modulation, also known as PWM, is a technique used to represent analog information or control power by varying the width of digital pulses while keeping the frequency constant. This makes PWM efficient. We will focus on two main processes, modulation and demodulation. Modulation, also known as PWM generation, is the process of converting a message signal into a PWM waveform. Demodulation is the reverse process where the original message signal is recovered from the PWM waveform. We study three demodulation methods, which is low-pass filtering, sample and hold conversion, and the integrator or ramp method.
After a brief overview of this video, I will introduce Pulse Width Modulation or PWM, which is the focus of my section. PWM is basically a technique widely used in modern electronics to control power efficiently. It can be found in many everyday devices such as LED lights, fans, and motor controllers. You might be wondering why PWM exists. Traditionally, power control was achieved by reducing voltage using resistors. However, this method wastes energy in the form of heat because resistors are passive elements. In addition, using potentiometers is impractical due to higher cost and the need for manual adjustment. PWM provides a more efficient solution by controlling power through rapid switching between fully on and fully off states. This reduces energy loss while still allowing precise control. So, what exactly is PWM? PWM is a clever way to control the average power delivered to a device by rapidly switching an electrical signal on and off. Instead of supplying a constant DC voltage like a resistor-based method, you can think of PWM like a light switch being flicked on and off very quickly. Instead of dimming the light by lowering the voltage, the switch sends pulses of power. The longer the switch stays on, the brighter the light appears. This on duration is known as the pulse width, and it determines the average power delivered. Because PWM switches between on and off states, the waveform appears as a square wave. As shown in the visualization, increasing the duty cycle increases the pulse width. As mentioned earlier, the key concept in PWM is a duty cycle. The duty cycle refers to the percentage of time the signal remains on during one complete cycle. A higher duty cycle delivers more power, while a lower duty cycle delivers less power to the load. Now, let's look at how PWM is actually generated. Don't worry, the concept is simple. PWM is produced by comparing a message signal, such as a sine wave, with a reference signal, usually a triangular wave. When the message signal is higher than the reference signal, the PWM output becomes high. When the message signal is lower than or equal to the reference signal, the PWM output becomes low. This comparison directly controls the width of each pulse. In this animation, the blue waveform represents the message signal and the green waveform represents the carrier signal. Whenever the message signal is higher than the carrier signal, the PWM output turns on. When it is lower, the PWM output turns off. From this animation, you can clearly observe how the pulse width changes according to the message signal. When the message signal has a higher amplitude, it stays above the reference signal for a longer time, resulting in wider PWM pulses. Conversely, when a message signal has a lower amplitude, the time span above the reference signal is shorter, producing narrower PWM pulses. This happens because the signals are continuous and change smoothly over time. Let's try a quick question. If the duty cycle increases, does the LED become brighter or dimmer? The answer is brighter, because more power is delivered during each cycle. So far, we have seen how PWM is generated by encoding information into pulse width. In the next part, my teammate will explain how this PWM signal can be demodulated to recover the original information.
As we just learned, modulation is the process of encoding information into a signal, so it can be transmitted or controlled. But once the signal has been transmitted or used, we often need to recover the original information, and this is where the demodulation comes in. Demodulation is the process of extracting the original message from the PWM signal so that it can be used in the system. And now, I will introduce how we demodulate PWM signal and explain the three common methods to do it. But before entering the way to demodulate, many people will be curious why we need to demodulate it. And the reason is, the information in PWM is stored in time, but not in the signal height. However, more of the system work better with smooth and continuous signals. Therefore, we need a way to extract the information from PWM. And there are three common ways to recover the information from a PWM signal. A simple way to understand these three methods is to look at which method is measuring and what is measuring. First, the low-pass filtering method is measure the average value of the PWM signal. Sample and hold is convert the pulse width into a signal height. and the integrator method is measure the area under each pulse. This difference explains why their accuracy and complexity are different, and you can think of them as three different ways of understanding the pulse. For the first method is the low pass filtering method, and it is also the simplest one among these three methods. In this method, we directly smooth the PWM signal. The fast switching pulse are averaged out, and what remaining is a smooth waveform. You can imagine it like a burning a fast flashing light until you only see its brightness. This method works well when you only care about the average level, but it's not very accurate. The second method is the sample and hold method. PWM store information in time, and which is harder to deal with. So, we first convert it into a signal where the high represent the information. We can say convert it to PAM. And once the information is stored in amplitude, it becomes much easier to filter and recover. This method gives better accuracy than simple averaging, but it requires the correct timing. The last method is the integrator method. This method measures how much the signal area each pulse contains. The wider the pulse means more area, and which means a higher output. This method is very accurate, but it is also the most complex to implement. And among these three methods, the sample and hold method is the best choice for our application. The reason we choose the sample and hold method is that it offers a good balance between the accuracy and the complexity. Compared to simple low-pass filtering, it gives us more accurate result with less ripple. And at the same time, it's also less complex than the integrated method and easier to implement in practical systems. Therefore, for systems that require reasonable accuracy without high complexity, the sample and hold method is the more suitable solution. And this page show the small conclusion and the comparison between these three methods. And next, we are going to talk about the application in the real life.
I will cover the topic of where is PWM used, is the technology evolving, and is it safe for us to use. So where do we use PWM? So I want us to imagine a world where we suddenly lost PWM technology right now. So what will happen? First of all, you will notice that your screen will drain battery very fast, and it will start to heat up, and you can't control the brightness. The same thing will happen in laptop, whereas your cooling fan can be controlled and it will be very loud. The LED light around your room will focus, and it won't be like dim or continuous light. And if you are sitting in the EV car right now, you notice that the car can't accelerate smoothly. PWM technology is just around us. Why is this technology so superior? So we need to see with how the technology is evolving. So PWS technology, they shifted from silicon transistor to wide bandgap semiconductors such as silicon carbide and gallium nitride. So this ensure or this enable us to have faster switching, meaning higher frequency of switching. It allows us to push the limit of megahertz. And this in turn help us to shrink the size of the inductor and capacitor. When both of the component is shrink, it allows us to have smaller filters. And smaller filters in electronic devices always result in better result. Why? Because when it is smaller, we could pack a lot more filters into the devices, and with smaller size, it could give us a higher capacity. So for example, your phone charger right now, if you look at the size, it's actually quite small when you compare it to the vortex that it actually provided. So a small device or small charger will charge your phone from 0 to 100 maybe in 30 minutes, right? So if we think bigger, when we think about in EV, we could also use or apply to technology in EV car, because like if we have smaller charger with higher capacity, then we could have portable charger inside of the car, and when we need emergency power, right, we could just use the charger. So after all the benefits, we need to start to wonder, does PWM technology poses health risk? The answer is yes, because of the invisible flicker. So if you see on your phone right now, like you probably can't detect the flickering. That's because like we can't actually detect flickering above 80 hertz. However, many screen dim, they uses low frequency. So for around 100 to 400 hertz, but still our brain can detect the pulses which may cause eye strain and migraine lah. How can we solve the problem? Because this is a convenience matter and this is a health matter. Phone company, they had the initiative to solve the problem. So if you look at their solution, they usually increase the frequency, like how they market their phone. You usually see that they market their phone by, oh, my phone has 1,000 hertz of PWM, or this phone had 2K, and then they are pushing 3K. And lately, they are pushing the limit to 4K or even 5K PWM. Because that above 1,250 hertz, our brain can't process the flickering and we could see the light as continuous. You may notice that they are using hybrid dimming, which is DC plus PWM. In lower brightness, they will use PWM, and in higher brightness or maximum brightness, they just use the DC because, right, in maximum, right, just use DC, it's constant. However, in places that have lower demand, such as the industry, where maybe there are a few workers using the PWM screen, how can we ensure their safety when using the screen? So we need to have stricter safety standard like the TUV Reinhardt certificate, which enforce strict limit on modulation depth, ensuring screens are safe for long-term viewing.
Before we end this section, let's scan the QR code and try out a quick quiz to test your understanding of
By
PWM.
comparing a message signal with a carrier waveform to generate the PWM signal, and how demodulation reverses this process by converting pulse timing back into a continuous signal. This shows how time-based modulation can be used to transmit or control information efficiently. We also discussed how PWM is deeply integrated into everyday technologies such as smartphones, laptops, lighting systems, electrical vehicles, and audio devices. We discussed how PWM technology continues to evolve with faster and more efficient switching devices like gallium nitride and silicon carbide, and how engineers are addressing issues such as screen flicker through higher switching frequencies and safety standards. Overall, understanding PWM modulation and demodulation helps engineers design systems that are efficient for modern electronic and communication systems. Thank you.